Can you guys hear me? Okay, let's start. So there are people who asked me about, like, they emailed me and asked, like, why we're doing geometry. I mean, people who do competition math a lot should know the answers because there are obviously lots of problems on the AMC 8 and AMC 10 that involve geometry, which is why we're doing it. So now, let's start with some basics. So, what are similar triangles? Well, we're going to cover these concepts because there are lots of problems that use these concepts. So similar triangles are, you can tell by the name, they're triangles that are similar. The three angles have to be the same for those two triangles to be similar. And in similar triangles, the ratios of the side lengths will always be the same for any two of the sides that are corresponding to each other. So you might be wondering about how to identify similar triangles. Well, there are three main ways. One of them, the most common one, is AA similarity, which stands for angle-angle similarity. In this method, I'm going to draw it out and show you guys what I mean. So pretend this is one triangle, which is a 3, 4, 5 right triangle. And then there's another one, which is a 6, 8, 10 triangle. Pretend we know that these are both Pythagorean triple, so this is a right angle. Pretend this angle is congruent to this one. Pretend it's 60 right now, and this is 60. So angle-angle similarity tells us that if two of the angles are congruent, then the third one, are the same, then the third one is also, which actually makes sense. So pretend if I change this angle to 50, and then I change this angle to 50, then this is going to be 40, and this is going to be 40. So do you guys get what I mean? They're both like, so that means if like two of the angles are the same, then the third one will also. It's just common sense, and it'll make sense after we do some problems if it doesn't make sense right now. Now the other one is SSS, which stands for side, side, side. In this theorem, it's basically that if all of the sides of the two triangles are proportional, then they are similar triangles. So basically, pretend I have two triangles. Oh wait, I'm going to draw a figure again to show what I mean. I want to show examples to you guys so it'll be a bit easier to understand. So pretend these are, okay, don't mind the angle measures, I'm just putting in random measures right now to show you guys what I mean. So pretend this is 3, oh my god, this is 4, 5, this is 3, this is 4, this is 10, this is 6, and this is 8. So what this means is that, are these two triangles similar? Well, they are, because, so what is the length of the angle opposite to the right angle for the second diagram? It's 10. And what is the angle? What is the length of the side opposite to the other right angle, which is 5? So you see that the ratio is just 2, and it's same for this. So 8 to 4, which is also 2, and 6 to 3, which is also 2. So that's what SSS tells us. So SAS. Now this is another very important theorem. But it's not used as much as angle-angle similarity. Angle-angle similarity, it's used in a lot of problems. SAS is basically, pretend I have two triangles. I'm just going to draw something random. This is 90. And then this is 90. So pretend, this is 3, this is 4, this is 6, and this is 8. So you might be wondering if these are similar or not, but the answer is yes, because we see that the included angle that is between both of the sides, they're both 90. And then the sides, so pretend this is 6, and this is 3, so 6 over 3, that's 2, and 8 over 4, That's 2, and they have the same proportion, the same ratio, which means that these triangles are similar. And now I'm going to show you guys a very basic example problem. This is just a very basic example so you can kind of like understand what I mean. So we see that this angle, whenever we don't care about what this angle is, but we know that it's congruent to angle C. Wait, so if this is congruent to angle C, and angle T is congruent to angle E, there's one thing we know. We're going to use angle similarity. But you don't also have to use that. We know that these angles, both of the triangles share the same angle, which is FV and FVT. So either way, we know that these two triangles are similar to each other. So we're gonna take FVT is similar to CVE. Okay. Also, not to confuse you guys, if you ever write a similarity statement, this is the similar symbol, and also it should correspond to the angle. For example, I have F here and C here. I'm not gonna write V here because V is not equal to F. We don't know if it's equal to F. So we write it to the we write it in order. It has to correspond to each other. And in this problem, so now these two triangles are similar, so we're gonna use proportions. So basically, we know that this is the first side length, which is 10, which is also equal, and then the other side. Now if this is x, now we need this side, which is just 15 minus x. We don't know it right now. We're going to solve for x though. Now we're going to take the other triangle, which is this one, FVT, and basically what is FV? It has to correspond to the other side, so it's basically FV is 16 because 6 was 10. Now what is the other length? It's 15 as it says. So now this is the statement, and it's just a one variable statement, so it's easy to solve. You multiply both sides by 15, it crosses this one out, 150, and then there's 15 minus x here. You can you also multiply that to both sides, so this thing crosses out, goes here. 16 times 15 is simply just 240 minus 16x. Now this is a very simple statement to solve. I'll take 16 to that side to make it positive, so it's easier to understand. So I add 16x to both sides, so I have 16x plus 150 is equivalent to 240. We subtract 150 from both sides, so 240 minus 150 is simply just 90. And then it's just time to reduce it. 90 over 16, and then if you divide by 2, you get 45 over 8. So x is just equal to 45 over 8. Now we're going to look at some harder examples from AMC 10 and those contests. Oh no, first I have to explain the angle stuff. So there are no formulas or theorems for angles, but there are some techniques to find out the angles. For example, the most common ones that you'll see are corresponding angles, alternate interior, same side angles, and vertical angles are just seen everywhere no matter what. Now some important terms are supplementary. A supplementary angle is basically two angles that add up to 180, and a complementary angle is two angles that add up to 90. I'm going to show you what I mean. So, okay, I'll just show you in this diagram. So we know 180 degrees. It's basically the angle measure of a line. So if you draw a line through that line, we're going to make these two angles are supplementary because they add up to 180. We don't care about the individual measure. We just want to know if they're supplementary or not, which they are. And a complementary is similar. It's just two angles that add up to 90. So pretend I have A, B, C, and this is D. And we know this is right, so we don't care about the individual measure. Okay, sorry about the messy handwriting. So all we care about are these two angles, complementary, and the answer is yes, since whether this is 30, this is 60, or this is 45, or this is 45, the sum is always 90, no matter what. So basically, if two parallel lines are cut by a transversal, then the corresponding angles are congruent. What I mean is, pretend these are two parallel lines, and this line is a transversal. I'll highlight it for you guys. This one is a transversal. So corresponding angles are congruent, which means A and E, F and B, H and D and G and C. And alternate interior are pretty similar. It's just this one, it's angles C and F, E, and D. You can see it down here also, over here. And then alternate exterior is just like similar to alternate interior, but it's just the outside instead of the interior. So it's A and H. You can see it over here. And now the total sum of any, oh, not shape, I mean shape. The total sum of any shape is n minus 2 times 180, and n represents the number of sides. So pretend I have a square. So based on our formula, it's any shape n minus 2. So the number of sides is n, and it's minus 2. So we're going to say 2 times 180 equals to 180. 2 times 180, which is 360, which means, so you can use this formula to find out the angle measure, the total sum of the angle measure for any shape. So now let's do some problems. So right triangle ABC has AB equals to 3 and BC equals to 4 and AC equals to 5. Square X, Y, Z, W is inscribed in a triangle ABC with X and Y on line AC and W on line AB and Z on line BC. What is the side length of the square? So whenever you see a geometry problem, you should try to draw it out first. So we see a right triangle ABC, and you should know your Pythagorean triples. 3, 4, 5 is 1, and it says that AC is 5, AB is 3, and BC is 4, and we know that this is a right triangle. It also says it there. And it says square X, Y, Z, W is inscribed in triangle ABC with X and W on line AC. So pretend X is here, and Y is here, and W is on line AB, so W is here, and Z is on line BC, so pretend Z is here. I'll make it a bit organized, and Y is here, and this is a square. It's very messy, but okay. So we want to find out the side length of the square. Now I see many similar triangles. Do you guys also see them? Well, basically we're going to use angle similarity to prove the triangle is similar. So and the angle the theorems that I told you related to the angles. So since we know that, pretend BWZ, we know that BWZ is similar to BAC. It's because WZ and XY are parallel to each other. The reason is that a square has two, the opposite sides are parallel to each other, and BC is the transversal, which makes the corresponding angles congruent. And we already know that this angle is a right angle because this is a square inscribed inside, and a square, these are basically both are supplementary, and this is 90. So it's X plus 90 equals to 180, and we simply get that the angle measures 90. Now pretend that the side length of the square is S, and the height of this triangle is H, because height for H, S for side length of square. So we want to write a proportion, again a proportional statement. So if these two triangles are similar, we're going to take some of the side lengths. So we want the total height of this figure. Well, there's another way of finding the height of this figure. Basically, heights of right triangles are also from the base drawn to the vertex, and it's going to also equal to the area. So we know that the area of 1/2 times 3 over 4, oh my god, 1/2 times 3 times 4, whatever the area of this is, it should also be equivalent to area of the triangle 1/2 times 5 times the height, so which is H plus S. Okay, I'm very sorry for being so messy. So we know that the area is 6, simply 1/2 times 3 times 4 is 6. So we know that whatever the height of this whole triangle is, the other height, it has to equal to 6. So we know that area is 6 equals to 1/2 times 5 times, we're just going to pretend it's not H plus S, it's H plus S is X, since it's easier to work with X. So it's just a simple equation you have to solve. So 6 equals to 5 over 2x. You multiply both sides by 2 over 5 to isolate the x, and then you get 12 over 5 as x. So now, since the height is 12 over 5, we're going to use that to solve the problem. So I'm going to erase the work that I've shown here, and I'm going to solve it right now. Now, since we know that the height is 12 over 4, this thing is 12 over 4 and the base is 5. I mean 12 over 5, I'm very sorry about that. So we know that the proportion statement is basically what we know, that there's a triangle here on the top, and we have to prove that this one is similar to this. So the height of this triangle, which is h, over the height of the bigger triangle, which is, we got it, it's 2.4. 12 over 5 is 2.4, which is equivalent to we have to find the base of this triangle, and we already know the base of the triangle. The base of that triangle is just the base it's just the side length of the square, which is s, over the side length of the bigger triangle, which is 5. And now we're going to use those two statements to try to prove the triangles similar. So after solving this, we're going to get 5h equals to 12 over 5s, but we already have but we know that the height is 2.4. No, it's actually easier to use one variable instead. So pretend I made a mistake here. So pretend the height is just x, so 1 is going to be x minus 2.4 minus x. So I'll show you what I mean. So we know that the height of this, so it's h minus s over s, because the height of the triangle and the side length of the square, which is also equal to h over 5. And then we have, and after solving this, we're going to get side length of 5h over h plus 5. I'm very sorry, I should have solved this also, but we have a lot more problems to go over. And then we already know that the height is 2.4. So we're going to plug that in there. So we have 12 over 2.4 plus 5, which is 7.4. 12 over 7.4 is the side length of the square. You can solve this out, but we have to do the other problems since there are a lot more left. So through a point on the hypotenuse of a right triangle, lines are drawn parallel to the legs of the triangle so that the triangle is divided into a square and two smaller right triangles. And the area of one of the two smaller right triangles is m, and the area of the is m times the area of the square. The ratio of the other small triangle to the area of the square is, we're going to solve this in terms of m. So we're going to write this up here, m. So we have a right triangle here. Pretend through a point on the hypotenuse of a right triangle, lines are drawn parallel to the legs. So pretend I choose this point, and then I have this parallel to this and parallel to this. So the legs of the triangle, so that the triangle is divided into a square and two smaller right triangles. So pretend the side length of the square is x, which means this one is also x. So pretend this is the smaller triangle, this one, I'll highlight it, this one. So this one's m times the area of the square. So the area is x squared times m. Now pretend this side length is y, so we're going to assume it's y. So we know the area of a triangle is 1/2 times the height times base, which is xy in this case, and we want to solve for y in terms of m. So we multiply by 2 first, and then we get 2x squared, m equals to xy, and then we divide by x on both sides to find the length of this in terms of m. So we get 2xm equals to y. So that means the side length of this is also equivalent to 2xm. We're also going to use some other triangles here, but first we're gonna I'm gonna show you. So this is x, and then based on the similar triangle ratios, pretend this is y. No, I mean z. Pretend this is z. So the ratio of x over 2xm, which is the other triangle, the two legs of this triangle, should be equivalent to the 2 legs of this triangle. So we're going to go with the base first, which is equivalent to z over x. So now all we have to do is multiply both sides by x, and we get x squared over 2xm equals to z. Now we see that one of the x's cancel out. So we have this side length is equivalent to x over 2m. But now we only have to find this in terms of m. So now it's just simple computation. So we have to find the ratio of this triangle to the area of the square. So we know the area of the square. It's just x times it. So I can explain better. So x squared over. So if the base of this is x over 2m and the height is x, we just go x over 2m times x times 1 over 2, which is simply just x squared over 4m. In this equation, in this problem, we see that the x squares cancel out, and we just have 1 over 4m left, and that is the answer. Now, the Pythagorean theorem, it's a theorem that is used a lot, very often. It's for right triangles. It states that the square of one side added to the square of another is equivalent to the square of the hypotenuse. So a squared, pretend this side is a, plus b squared equals to c squared. Maybe right now you're a bit confused about what this is, but after I show you some examples, it should start to make some sense. So the diameter line AB of a circle of radius 2 is extended to the point outside the circle so that BD equals to 3. So as soon as we see a circle, the diameter, that means there's a circle. So the diameter line AB, pretend this is B, of a circle of radius 2. So if the circle has a radius of 2, the diameter is just 2 times the radius, which is 4. Now point E is chosen so that, point D, so that BD equals to 3. So pretend D is here. We know that BD is equivalent to 3. And ED, there's a segment ED, which is perpendicular to line AD, which means that it can't be like this or this. It's perpendicular, which means that it makes a right angle. So pretend point E is over here. Segment AE intersects the circle at point C. So pretend this is a segment and it intersects this at C. So now we want to find out the area of triangle AB and ABC. I want you guys to try to solve it. Okay, so this problem is actually very hard if you don't see this trick, but there's one trick to this problem. So we know that ED is equivalent to 5. So we want the hypotenuse of the bigger triangle, which is just 7 squared plus 5 squared, which is equivalent to, that's so that's square root of 79. With the Pythagorean theorem, AE is equivalent to the square root of 79. And we know that this is a right angle because any triangle that is drawn and the hypotenuse is the diameter of the circle, and the third point is anywhere on the circumference of the circle, then it's a right angle. So since we know that this is a right angle, we're going to use similar triangles. And we know that these are similar because we see that this angle of ACB is also used by this other bigger triangle. So all we have, and there's another thing I forgot to tell you guys about. So basically, if there's any triangle, the ratio of the areas is basically the ratio of any of the side lengths squared. So we could use algebra to solve this out, but it's going to be very complicated. This is going to be square root of 79 minus x. You know, this just looks too painful to solve, and we don't want the problem that we're solving to be that painful, or else it's going to be a little bit too hard. So we're going to have to think of something smarter, which is, as I said, the ratio of the areas is basically the ratio of one of the side lengths squared. And we know that the area of this triangle is just 7 times 5 over 2, which is 35 over 2. And then there's another thing that we know. We know that these two triangles are similar, and we have the hypotenuse of both triangles. It's just 4 is the hypotenuse of this, since it's the diameter, and it's square root of 79 for the bigger one. So it's 4 over square root of 79 squared times the area, and that is the area of triangle ABC. So what is 4 divided by square root of 79 squared? That is simply just 16 over, since if you multiply two square roots, the square root's just gone. So 16 times 79 times 35 over 2. So that is the area of ACB. So you cross out 2. So 8 times 35, which is 140 over, no, I'm so sorry, 280. Oh, I'm very sorry, this is 74, right? This is a 79, so 280 over 74, and you reduce this to get 140 over 37, which is the final area of the triangle. So you see how we applied the fact that the ratio, if two triangles are similar, then take the ratio of one of the side lengths and square it, and that is the ratio of the areas. So that's what we use to find the area of this triangle. Well, the second problem, in triangle ABC, we have AD, AB equals to 6, AC equals to 8, and BC equals to 10. You should know your Pythagorean triples. With this, we know that these two triangles are, what's that called? It's a right triangle. So, pretend this is B, this is C, it says BC is 10, this is A. AB equals to 6, AC equals to 8, and D is the midpoint of BC. Whenever I see midpoints, I start thinking about medians. So it's the midpoint of this line, and then we have the radii of the circle inscribed in triangles ADB. Look how I want you guys to try to solve this problem, and after that we'll see the solution. Okay, it seems like I do math got that AD is equivalent to 5, and he's perfectly right. So we're going to use one of the theorems that if there's a midpoint, we know that this is the midpoint, since it's this is the midpoint of this side. So if you draw lines, straight lines like parallel to the other sides, like this, then the segments are just half of the lines that they're parallel to. So if these segments are half the size of the other of the segments that they're parallel to, we know that this is half of this, of half of 6, which is 3, and this is half of 8, which is 4. Now I start seeing some Pythagorean triples. We know that this is going to be 4 This is also going to be 4. I'm going to erase the 8 to make it a bit understandable. And then we divide this. We know that this is 3 and this is 3. So using that Pythagorean relationship, we know that 3 squared plus 4 squared, which is 25. Square root of 25 is simply just 5. But now now it's asking for the radius, which is the hard part. But now I'm going to tell you guys a theorem. Basically, the radius of any triangle. Pretend if there's a circle inscribed in the triangle, then whatever the radius of that circle is, the radius times the semi-perimeter is equivalent to the area. So now I have R1, which is the radius of the one circle, and R2, which is the radius of the other circle, which is also equivalent. This is another way of saying the area. So how are we gonna find the area? Well, that's pretty simple. We know that the height of this triangle, the semi-perimeter, we know this is 5 plus 5 plus 6, which is equivalent to 16. But the semi-perimeter is exactly you have to divide it by 2. So it's going to be 8 times the R1, which is equivalent to the area, and the area is just the base, which is 6, 3 plus 3 times 4, 24 divided by 2, which is 12. And for the other circle, which is this one, we know that the side lengths are 5 plus 5 plus 8. 5 plus 5 is 9. So we know whatever this area, this is 9 times the radius, which is the second radius, which is R2, which is equivalent to the area of this triangle. The base, the height is 3, the base is 8, so 8 times 3 is 24, divided by 2, which is equivalent to 12. Now we have to find the sum of the radii. So we know that we just divide 8 on both sides. We get 12 over 8 plus 12 over 9, since we divide 9 to both sides to get the radius of this one, which is just 4 over 3. I just reduced 12 over 9 there. Now we just have to find the LCM, which is 24. You solve this problem, and you're going to get 68 over 24, and you reduce this further, and you reduce this one more time, and the final answer is 17 over 6. So you saw the theorem about how to find the area of any inscribed circle in a triangle. It's just R, the radius, times the semi-perimeter, and that's what we use to solve this problem. It's a very helpful thing to remember. So this is an problem from AME 1 from 2006. In a quadrilateral ABCD, angle B is a right angle and diagonal AC is perpendicular to line CD. As I said, whenever you see a geometry problem, draw it out. So there's a quadrilateral ABCD. Pretend angle B is this right angle, and this is angle A, and this is C. So it says that diagonal AC is perpendicular to CD. So pretend this is D, since we have to imagine this a bit. So this is 90. Well, this is perpendicular to D, and we want to find the perimeter of the shape. So now let's see the side lengths it gave us. We know that AB is 18 and BC is 21 and CD is 14. Now using these side lengths, we're going to find the perimeter. So we want to find out this length first, AC, which is simple Pythagorean theorem. 18 squared plus 21 squared. Pretend this is x, which is equivalent to x squared. So we know that 18 times 18 is just 324 plus 21 times 21, which is simply just 441, which is equivalent to x squared, which adds, and these two numbers add up to 765, so equals to x squared, and then you square root both sides, you get x is equivalent to 765. We're not gonna simplify this right now because we want to find out 80 first. And to find out 80 first, we have applied the Pythagorean theorem again. So 14 times 14, 196. Pretend this is y. So 196 plus square root of 765 squared, which is just 765, which is equivalent to y squared. And then you add these two up, and you get 961 equals to y squared. Now you have to find out the square root of 961 to find out the other side, and that is 31. So see, this AIM problem, we cracked it out using the Pythagorean theorem. Now all we have to do is add up all 4 of these sides. So 18 plus 21 plus 31 plus 14, which is simply just 84. But this is AIME, so you have to write a 0 before. So 0 and 84. I'm going to check the chat just to see if anyone has questions. Okay, it's time to move on. So square ABCD has a side length of 1. And points E and F are exterior to the square such that BE equals to DF, which equals to 5, and CF equals to 12, and AE equals to 12. Now I want you guys to try to solve this problem. Okay, sorry, I accidentally meant that this is 13, not 1. So these are actually 13. So the best part about AIM problems are that, competition math, this is not school math. You don't need to show your work. You need to do it the way you want to do it. But if you look at this shape, doesn't it look like you can form a square here? I'll show you what I mean. I see this. This is what I see. Now, do you guys get what I mean? Now try solving it. Now, did you see how we turned such a complicated looking problem into just a normal square? Now, we want to find EF. Now, EF is just one of the side lengths plus one of the side lengths squared. Both are squared, added together, and that's the square root of it. So it's very simple now. So now we know this is 5, and these are all congruent triangles. So if this is 5, and this is also 5, and this is 12. Now, if we want to find EF, we add 12 plus 5, which is 17 squared, plus 17 squared equals to, pretend this is x, which is x squared. And then this adds up to the square root of 578. Now we want to find EF squared. This is EF. Now EF squared, if you square a square root like a length, then the square root just goes away, which makes it 578. So now that means if you see a geometry problem, draw around. It's actually good to draw around. You're gonna see these wonderful solutions that you can never even think of, which if you try it. But if you just think and look at it, then you're not gonna find that solution. Now, finding the area of many shapes in these problems can look very hard, but looks are deceiving. There is one trick. You need to draw it in the problem, as I said. Draw inside the shape, draw around. So a lot of problems you can solve if you try to draw triangles inside. Trust me, you need to draw triangles inside. A lot of the problems can be solved by just drawing triangles inside, which is very important, as I said. You need to try it. For example, this is a very good problem. So the figure below shows 13 circles of radius 1 within a larger circle. All the intersections occur at a point of tangency. What is the area of the region shaded in the figure inside the larger figure? So I want you guys to try solving this problem. Okay, it seems like many people get the idea of how to solve it. It's all about drawing triangles. So we know that all these points are tangent. So in a lot of circle problems, look at the centers. The centers, you can make lots of triangles with those. So if you connect these centers, okay, sorry about the messy line. We see that this is just an equilateral triangle with a side length of 6, because 2 diameters plus 2 radiuses. 2 radiuses equal to 1 diameter, which is just 3 diameters, and each diameter is 2. So the entire length is 6. This is 6, and this is 6. Now the height. If you make a perpendicular line, you're gonna divide this length by half. So this is 3 and this is 3. And now to find the height, you just do the Pythagorean theorem. 36 equals to 9 plus x, pretend this is plus x squared, and then x squared equals to 27 because you subtract both sides by 9, and then you get 3 square root of 3 as the height till here. Now now we're gonna use that information to try to find the entire height. So we also know this length. This is just 1. It's the radius, so it's 1 plus 3 square root of 3. Now we need more triangles, and then, as I said, you connect more centers. And I'm going to show you what I mean. We already have the length to here, to the top. We already found out the length here. But if you draw another triangle here, you'll see that we get another equilateral triangle with side lengths of 2. Now, if you divide it by half again, as I said before, the length is half of it, so 1. So it's just 4 equals to 1 plus y squared. Y squared equals to 3. Y equals to square root. Y equals to the square root of 3. Now, if this is the square root of 3, we know this segment is just 1. It's the radius again. So 1 plus 1, which is 2, plus the square root of 3 plus 3 square root of 3, which makes it to 4 square root of 3. So now that is the radius. That's the diameter of the bigger circle. So now, if that's the diameter, what is the radius? It's just 1 plus 2 square root of 3, which is the radius of the bigger circle. And then we want to find out the shaded area, so we're going to find out the area of the bigger circle first. Let's do that right now. So what is 1 plus 2 times square root of 3 squared? That's basically pi, because pi are squared. So you also multiply pi to each other after squaring each term, and then you're going to get plus 12 pi plus 4 square root of 3 pi, which is 13 pi plus 4 square root of 3 times pi. So now you have to subtract by the total area of these circles. Now if the radius of each circle is 1, so it's just pi r squared. So each circle is pi, and there are 13, so 13 pi. These pi's just cancel, and we get 4 pi times the square root of 3, and that's the answer. So you saw how like drawing triangles brings in the answer after. Now this is another very important this problem. It's just about reading what it says. So let AB be a diameter of a circle, and let C be a point on AB with 2 times AC equals to BC. So pretend pretend BC is 4x. It says that AC is 2x because it's just half of BC with that information. The reason why I'm using 4x is because if I use something else, like pretend I use just x, then this is going to be in fraction terms, and we don't like fractions. So 2x plus 4x is 6x. Now 6x is the diameter, so that means the radius is 3x. And it says that D and E be points, and it says that so that DC is perpendicular to AB, and it says that AB and DE and DE is a second diameter, which means that we already found out the diameter is 6x. And whenever two radiuses intersect, the point that they the two diameters intersect, the point that where both of the diameters intersect, that's and if you draw lines out, that you get the radius. So using that, you know that these are 3x. Now we want to find out the ratio of the area of triangle DCE to the area of ABD. ABD is a bit easier to calculate. The height is, so basically if the segment A to here is 3x, and this is 2x, so 3x minus 2x is just x. So now if we know that this is x, we're going to use the Pythagorean theorem to find out this. So 3x squared, which is 9x squared, minus x squared, which is 8x. So we simply get 2x times the square root of 2. And then if you multiply this by 2, we get the whole length, which is, this is also 2x times the square root of 2. But we want to find out the area of ABD, which is 1/2 times the base, which is the diameter, which is 6x, times 2x times square root of 2. So we see that this is just 3x times 2x squared root of 2, so 6x squared over square root of 2. Now we want to find out the area of the other triangle DCE, which is just simply the base. We know the base is 4x times square root of 2, and the height is times 6 times 1/2. And after you multiply out, you get 2x squared times square root of 2 divided by 6x squared times square root of 2. Now the root 2's both cancel out, so we just have 2x squared over x squared. The x squares cancel out, so we have 2 over x, and 2 over x is equivalent to 1/3. So the ratio is just 1/3. Now these I'm going to show you guys two triangles that are very important in mathematics, especially this competition math. It's 45-45-90 triangle. It's basically a right triangle that is isosceles. Two of the angles are 45 and the other is 90. So pretend I have this is 45, this is 45, and this is 90. So pretend this is 2 and this is 2. No, the side opposite to 90 is just a times square root of 2 of one of the side lengths, which is 2 times square root of 2. So it's 2 root 2, which is and for 30, 60, 90 triangle, it's just another right triangle, and these are the lengths that are, so the length opposite to 30 is just x, and the length opposite to 90 is a double of x, and the length opposite to 60 is square root of 3 times x. I would really recommend memorizing this one, because the 45-45-90 triangle, you can find that out in the exam without knowing that it's just x times square root of 2. But if you're trying to on an exam, it's very hard to find out the 30-60-90 relationship, which is why I recommend memorizing that. So we're going to solve a problem which is pretty hard if you don't know 30-60-90 triangle, the relationship between those 30-60-90 triangles. So we know that in rectangle ABCD, AD equals to 1, P is on line AB, and DB and DP trisect angle ADC. Now, we know that bisect means that it divides it in half. So trisect, it's going to mean it divides it into 3 equal pieces. So we want to find out the perimeter of BDP. So using 30, 60, 90 triangles, we know that if a rectangle, all of the angles are 90 and it's divided by 3, since all of these are congruent. So these are all 30. We know this is 90 because it's one of the angles of the rectangle. So 90 plus 30, 120. The total sum of all the angles of a triangle is 180. So 180 minus 120 is 60. So we formed a 30, 60, 90 triangle, and now it's just some computation. So we know that first I'm gonna show you. I'm gonna label all the angles. This is 120 because 180 minus 60 is 120. 120 plus 30 is 150, and it's you subtract that from 180, you get 30. So basically, the angle opposite to so pretend 30 is x, and 60 we know that's x times square root of 3, and this is 2x. So if the opposite of 30 is just x, we know that whatever x is, x times square root of 3 equals to 1. So then we're going to find out the other lengths. So x equals to 1 divided by square root of 3. And that is the side length we wanted. We can rationalize this, but we will do it in a bit. So we know that this is 1 times the square root of 3, 1 over square root of 3, and we know that dp is just 2 times that. So 2 over square root of 3. We know that this is also 2 over square root of 3 because this is an isosceles triangle, 30 and 30, and the angle, and that means that the sides opposite to both of the angles are going to be congruent. So now we're almost there to the end of the problem. We know that 2 plus 2 over square root of 3 plus 2 over square root of 3 is 4 over square root of 3. Now to find BD, we know that that's just the hypotenuse of BC, of just ADB. So BC is 1. Now I'm going to solve it here since it's a bit, like, it's just more organized. Oh, I forgot to label this out. X is 1 over square root of 3, which means that this whole length is 3 over square root of 3. Now finding out the hypotenuse is pretty easy. Now I'm going to rationalize it. So 3 square root of 3 over 3. Rationalizing, if you don't know, it's like basically, so we don't want, for those who don't know, we don't want square roots in the denominator, so we multiply the denominator by the denominator basically to both sides. So times square root of 3 times square root of 3, which is equivalent to 3 square root of 3 over 3, and then you cross 3 crosses out, so this is square root of 3. Now to find out this length, it's just 1 squared, which is 1, plus square root of 3 squared, which is 3, which is equivalent to 4, but you square root that, and that is the side length of BD. And we know that square root of 4 is just 2. 2 plus 4 square root of 3. On most of these exams, you will need to rationalize the denominator for the final answer. So you multiply both sides by square root of 3, and you get 4 square root of 3 over 3, and that is the final answer. Now this shows that it's very important to know your 30, 60, 90 triangle pairs. Well, it can be a lot harder to find out the answer to some of these problems. So this is another very good problem. I want you guys to try this. So now I'll just draw the diagram. We know that rectangle A, B, C, D, AB equals to 6 and BC is equivalent to 3. Now we know that point M is chosen on side AB, so that AMD equals to angle CMD. So pretend I choose M here. AMD equals to CMD. And we want to find out the angle measure of AMD. So to find out, to find the answer, we're going to use some variables. So pretend AMD is x. That means this is also x. Now try solving the problem. Maybe now you guys can get it. If not, that's perfectly fine. Okay, so basically the idea behind this is I showed you guys in a previous slide that if two parallel lines are cut by a transversal, then alternate interior angles are congruent, and we're going to use this idea here. Now AB and DC are two parallel lines, MD is a transversal. Now we know that if this is x, then this is also x due to the alternate interior angle theorem. So now if this is x and this is x, we know this is an isosceles triangle, which means that whatever side is opposite to x, which is 6, is also opposite to this one, which is 6. Now we know that this is a right angle. So now all we need to do is find out MB, and then we're going to see if we get a relationship between the angles and the sides. So 6 squared, which is 36, minus 9 equals to, pretend this is x, pretend this is just y, which is y squared. And then y squared equals to 27, which y equals to 3 square root of 3. Now if this is 3 square root of 3, I mean, you can try solving this problem and finding the angles, but it's going to take more time. Instead, there's a more clever trick. If you remember your 30, 60, 90 relationship, you'll remember that the angle opposite to 30 and the angle opposite to 90. The 91 is 2 times the one opposite to 30. And the 61 is square root of 3 times the one opposite to 30. So we see the relationship, the 30, 60, 90 relationship in MBC, triangle MBC. Now if this is 30, that means 180 minus 30 equals to 2x, and 180 minus 30 is equivalent to 150. 150 equals to 2x. Now you divide both sides by 2, and then you get x is equivalent to 75. So AMD is just 75. So now I hope you see the importance of knowing the 30, 60, 90 triangle relationship. Triangle ABC has a right angle at B, and AB equals to 1 and BC equals to 2. The bisector of angle BAC meets BC at D. What is BD? Now this we know if the bisector of angle BAC meets BC at D. Now, if this angle is bisected, that means these two angles are congruent, because bisect means it divides the angle into two equal portions. So, based on this theorem, we know there's a theorem I'm going to tell you guys about, which involves the bisector thing. So basically, this side length is 1. I'll show you guys the theorem first. So pretend I have a right triangle. It can be on any triangle, and I divide this angle in half, like it's bisected. So pretend this is A, this is B, this is C, this is D. So the theorem states that A over B will be the same ratio as C over D. No, it's not A over B equals to D over C. You do, if you're doing the side length opposite to the bisected angle first, then the other side should also be the side length of the bisected angle first. You get what I mean. The order has to be the same. You'll see what I mean when I show you guys an example. So we want to find out this length. So it's the answer, the way to solve this problem is AB over BD, and X is the length of BD. So we want to find for X. So I'm going to circle X here so we know what we're looking for. So you multiply both sides by 2 minus X. to get rid of this one, and then you multiply both sides by x to get rid of this one. You get square root of 5x. Now we want x to be on one side of the equation, all of the x variables that have x squared of 5 times x plus x. Now using this theorem, we know that, we're going to factor this out. I'm going to erase my work here so I can. So basically, so that means x times the square root of 5 plus 1 equals to 2. Now the side length of BD is just x equals to, you divide both sides by square root of 5 plus 1, so you get 2 divided by square root of 5 plus 1. This is not going to be an answer choice because, as I said, you need to rationalize the denominator. In this case, you don't just multiply square root of 5 plus 1, you multiply square root of 5 minus 1, so you can cancel out. You'll see what I mean. Whatever the symbol is, you multiply to the opposite symbol. So times the square root of 5 minus 1 times square root of 5 minus 1, you get 2 square root of 5 minus 2 over square root of 5 times square root of 5 is 5 minus 1, which is 4. So basically, now this is x. Now you see 2 is common in the entire thing. Oh, this is wait. So basically, square root of 5 minus 1 over 2. You divide. So the answer is square root of 5 minus 1 over 2 because this whole thing can be divided by 2. And that's how you get the answer. Okay, this is a very easy problem. I just want to show it to you guys to show that there are multiple ways of solving, multiple heights in a triangle, and this is just an example to show that it's a very easy problem. I just want to show you guys. So basically, given a triangle with side lengths 15, 20, and 25, note that this is a Pythagorean pair. 15, 20, a Pythagorean triple. So 15, 20, 25. Since we know that 25 is just 15 squared plus 20 squared, and square root that, it's 25. So this is a right angle. And you want to find the shortest altitude. To find the shortest altitude, you basically, since the area, so you just use the longest base length. So you use the longest base length to find it, which means the area, we're going to use the area of the triangle. Pretend to find the shortest altitude, there needs to be the longest base length. So this is the longest base length, so the height is x. We want to find this length. And then we notice that this is another way of finding the area of the triangle. 1 over 2 times 25 times x, which is also equivalent to, now that's the area of this triangle, which is also 150. Because 20 times 15 divided by 2, which is 150. So 25 over 2, 25x over 2 equals to 150. Now you multiply both sides by 2, 25x equals to 300. Now x, now we divide both sides by 12, and 25, and you get x equals to 12. Now we're gonna do some harder problems, but you guys are gonna solve it. You guys are gonna solve those problems, and I'm just gonna solve it after someone gets the answer. So this is the first problem. Take your time and try to solve it. Okay, I'm just gonna draw the diagram. So square A, B, C, D. I'm just gonna draw the diagram. So square A, B, C, D. Point E lies on the side, and point F lies on side BC, and E lies on AD. so that BE equals to EF equals to FD. So pretend this is E and this is F. Then all of these are 30. Okay, now I want you guys to solve this. Okay, I'm gonna show you guys a method to solve this problem. So in a lot of these problems, you make more triangles, and we're going to make these triangles. So we have 6 triangles of equal length, and pretend this is x. The side length is x. This is x, and this is also x, which means that this adds up to 3x. So this is 3x. Now this problem is actually very simple, because all we have to do, we found out if this is 3x, this is x, and this, which means, and this is 30, so this is just a Pythagorean equation that we make. So 3x squared, which is 9x, 3x times to the power of 2, 9x squared plus x to the power of 2, which is x squared, which is equivalent to 30 squared, which is 900. Now 10x squared equals to 900. Now you divide both sides by 10, and you get x squared equals to 90. So now if x equals to 90, we know that x squared equals to 90. X is just square root of 90. This is equivalent to square root of 9 times the square root of 10, which is 3 square root of 10. Now if that is 3 square root of 10, we need to find 3x. And 3x is just 3 times this, which is 9 square root of 10. So this is the side length, and now we square it. So 9 times 9, 81. Now if you square a square root, like that thing, the square root of 10, it just becomes 10. So 81 times 10, which is just 810. And now this is the next problem. Try solving it. And meanwhile, I'll answer some questions if people have any in the chat. Okay, we're gonna move on. I'm gonna draw the diagram for you guys. So basically, there's a rectangle which is A, B, C, D. So remember, it's a geometry problem. We draw it out. This is A, B, C, D, 20 and 10, because AB is 20 and BC is 10. So let E be a point on CD such that angle CBE equals to 15 degrees. What is AE? This is 15. and you want to find the length of AE. I'm gonna let you guys solve this now. Okay, now this problem is gonna highlight the importance of drawing in a geometry problem. We like triangles, as I said. A lot of problems involve drawing triangles. But not just any triangle. How about some special triangles, right triangles? We like those. We like 45, 45, 90, and we like 30, 60, and 90. Well, in this case, let's try 30, 60, 90 first. Now pretend this is 30 and this is 60. And there is a theorem that states that if two parallel lines are cut by transversal, then the same side angles are supplementary, which means that they add up to 90. But in this case, it's for complementary angles, so we know that 15 plus whatever this angle is, it's 75, which is 90. We know that this is 15 then. If we assume this is 60 and this is 30, boom, and this is 90. We made a 30, 60, 90 triangle, which was the trick to this problem. Now, the opposite to 30, the side opposite to 30 is just x, the side opposite to 90 is 2x, the side opposite to 60 is x square root of 3, and the side opposite to this is 2x. And now, you add both of these side lengths, and you get what x is equivalent to, which is what we want in this problem. 2x plus x square root of 3 equals to 10. Now x is equal to 2 plus square root of 3 equals to 10. I want you guys to try to find AE now. Try solving it. Okay, now it's just simple computation. Now all we have to do is divide both sides by 2 plus the square root of 3. So 10 over 2 plus square root of 3. Now remember what I said, rationalizing the denominator. So we do the opposite symbol if there are two terms. The opposite to plus is minus 2 minus square root of 3 times 2 minus square root of 3, which is simply just 10 times 2 is 20 minus 10 square root of 3. Now 2 times 2 is 4, and then square root of 3 becomes just 3 minus, so 4 minus 3 is 1. So this is just 20 minus 10 square root of 3 is x. So we know that this side is 10 minus 10 square root of 3. Now we want to find out this segment. Now this is simply just 20 minus 10 square root of 3, which is 20 minus 20 minus becomes a plus 10 square root of 3. Now the 20's cancel and we get 10 square root of 3. Now we're close to our answer. Now we have 10 here. And now we're gonna, this seems like a 30, 60, 90 triangle to me, but let's see. So 10 squared is 100 plus 10 squared times 3, which is 300, which is equivalent to 400. And then the square root of 400 is 20. Aha. AE is just 20. So you see how drawing other triangles inside can actually help it. We drew a 30, 60, 90 triangle inside, and then noticed that 15 and 15 they're isosceles triangles, and then this became just simple algebra. Now, this problem is very easy compared to the other ones, so I'm going to solve this one instead. And the next one you guys are going to solve. So triangle AMC is isosceles with AM equals to AC. Medians MV and CU are perpendicular to each other. MV and CU equals to 12. What is the area of the triangle? Now this problem brings in a very important theorem. So we know that these are the medians. So basically, if you draw another length, which is the median of the other median, there's three medians in a triangle, then this is the point where all three of the lines meet is called the centroid. The centroid. Now this might seem like why is it useful, but this is actually very useful because a centroid divides, if you add three medians, I'll write this down. If there are, divide the triangle into six equal shapes. They all it divides it into three equal shapes, and they all have the same area. They have the same area, which is the point of this problem, and the ratio is 2 to 1 where it's divided. Now, if we know it's 2 to 1, we know that wherever this MP is 2x, it's a PV, which is x. But we already know what 2x and MV is 12. So simply 2x plus x is 3x equals to 12. So x equals to 4. And the same applies here. So this is x and this is 2x. So x equals to 4. So MP is 8, UP is 4, PV is 4, and PC is 8. I'm going to erase and make it organized. 8, 4, 4, 8. Now remember the diagram I told you about. Look, if three medians intersect each other, like three medians of a triangle, they divide the triangle into 6 equal pieces, equal shapes. They have the same area. So if you find the area of one of them, which pretend this one, pretend if you find the area of this, then that's just 1/6 of the entire triangle. So then you just multiply by 6 and you get all of it. So this is just simply this is 90 degrees because it says the medians are perpendicular to each other. So it forms a 90-degree angle, and then we just know it's simple. It's just 1 over 2 times 4 times 8, which is 16. Now this is 1/6 of the entire. Now if this is 1/6 of the entire triangle, we just multiply by 6, and you get 96 is the area of triangle AMC. Now this next problem, I think this is the most important problem. I'm going to give you guys a long time to solve this one. Okay, I'll try solving this problem. This is a very beautiful problem. It has a very elegant solution, and you'll realize that it's just a very simple problem at the end, but it looks very hard. Yeah, I'm just gonna give you guys a clue. Triangles. Just remember, geometry, a lot of it is just revolving around triangles. Just think triangles, and you might find the answer. Okay, now let's look at the solution. So two skaters, Ali and Billy, are at points A and B respectively. The distance between A and B is 100 meters. Ali leaves A, skates at a speed of 8 meters per second on a straight line. That makes a 60-degree angle with B. Whenever I see 60, I think maybe an equilateral triangle or maybe 30, 60, 90 triangle. Maybe that's not the case, but we'll see. And then at the same time, Ali leaves A, Billy leaves B at a speed of 7 meters per second and follows the straight path that produces the earliest possible meeting of the two skaters. We have to find the earliest possible meeting of the two skaters given their speeds. But this problem is some algebra. So basically, they're gonna meet at the same time. Pretend they meet here. So let's draw a triangle for fun and see if that works out or not. Okay. Now Ali is traveling at a speed of 8 meters per second, and the other person is traveling at a speed of 7 meters per second. But at this point, they're both gonna reach at the same time. So pretend this is just the total time they all take is x. They each take x, 7x and 8x. Now I want you guys to try solving this problem. Okay, I'm gonna show you guys the way to solve this problem. It's all about 30, 60, 90 triangles. So basically, pretend we make a line all the way down here, which is straight, which means it's perpendicular to AB. This makes a 90-degree angle, and since this is 60, 90 plus 60 is 150, which means this is 30. Now this problem should be a bit easier to solve, because we have found ourselves our 30, 60, and 90 triangle. Now the side opposite to 8x, 90 is 8x, and the side opposite to 30 is always half of the side opposite to 8x, which means this is just 4x. And the side opposite to 60 is the square root of 3 times the side opposite to 30. So this is 4x times the square root of 3. And we already know a to b is 100, so this is just 100 minus 4x. Now, this is just simple algebra. Now, we'll just take this equation. The reason I'm not taking this triangle to solve out x is because it's just going to come out as 0 at the end. I'll show you why. 64x squared equals to 16x squared plus 48x squared. 48x squared plus 16x squared is 64x squared. 64x squared minus 64x squared is 0. We're not going to get anywhere if we use this triangle, so we have to use this triangle. So, using the Pythagorean theorem, this is the hypotenuse, so this is 49x squared equals to 4x times the square root of 3 squared is just 48x squared plus 100 minus 4x squared, 4x to the power of 2, which is 10,000 minus 800x plus 16x squared. Now after you subtract 49 from both sides, you should get 15x squared minus 800x plus 10,000 equals to 0. I mean, there is another way of solving this problem. It's a lot easier. It's using trigonometry, the law of sines, and stuff like that. But this is AMC 10, and we don't want to use trigonometry, and we want to find out another solution. Because using trigonometry isn't that fancy. But this problem, I mean, yeah, this method is the factoring can take a bit more time, but this method is called brute force. So there's a lot of calculation. But remember that on the AIME, you have 15 minutes to solve each problem. Average, I think, yeah. No, I don't remember how many problems there are, but you have a decent amount of time to solve each problem, and this is like number 6, I think. So you have enough time to solve it, even if you use this factoring method. So you divide 5 this whole equation, you get 3x squared over 60x plus 2000 equals to 0. Yeah. I mean, yeah, you can use the quadratic formula, but that's too much. That's too much mathematics. Like 160 squared, and it's gonna be a lot of calculation. But if you just try, we know that this is just gonna be x times 3x no matter what. And then we just have to try factoring out, and hopefully you see that. Maybe this is just. I'm gonna try out some pairs. So at the end, after you factor this out, you're going to get x minus 20 times 3x minus 20 to 3x minus 100. The reason why I'm not going to show you guys how I got this is because this is just a geometry class. The one for related to algebra and stuff is going to be in 2 weeks. So after you, we know that x is 20 for this one, and x is 100 over 3. Now we have to choose which one we want to use. And the way we're gonna do that is to see which one is less, because these both of them will work. We want to see we're gonna use the one that is smaller. So 100 divided by 3 is about 33.3 with the bar, which means 3 keeps going on, and 20 is less, so it's 20 seconds. We read the problem. It says how many meters. So 8 times 20 is 160 meters, and that's the final answer to this problem. So you see how using like looking for 30, 60, 90 relationships and all those triangles, you can find out the answer after that. I recommend just look for 30, 60, 90 triangles and triangles, because a lot of geometry revolves around triangles. Next week we're going to do circular cyclic geometry and 3D dimensional geometry. Well, in the circular one, we're going to be using lots of triangles. So triangles is a very important method. Now I'm going to be sending out a mini raffle link in the chat for people. And I also apologize for for the maybe it wasn't as entertaining as it should have been, but the reason is that I'm new to these classes and streaming, so it's just I was a bit nervous, but I'll try to make it better from now, and you can count on me. Thank you so much for coming, everyone. Next time I'll make it better than what it was today. I'm very, very sorry. I don't know how to apologize, but yeah, thank you. Thanks.